this electric field made by the negative charge. The negative charge makes an electric field pointing towards it, and so the dipoles are polarized this way. Positive charge is closer to this negative charge. And then just the size of the dipole indicates the strength. The field should get smaller the farther away you go, and the polarization, the dipole moment is proportional to the electric field. And also the direction. The direction in which it polarizes lines up with the electric field. Okay? So, no problems there. What about this one? Let's say you have a solid plastic ball, and now you take a negative charge and spread it uniformly over the entire surface. And remember that the electric field inside a uniformly charged sphere due to charges on the sphere is 0. Which diagram best shows the polarization of the molecules inside the ball? All right, and 72% of you fell into the trap. So let's think about this. Now this is sort of a little factoid that you actually was in the book in the last chapter. Well, let's talk a little bit more about it now. If you have a sphere, okay, and the sphere is uniformly charged, okay, doesn't matter whether it's a conductor or an insulator. We're just talking about the geometry here. The geometry is uniform charge spread over the entire sphere. The electric field due to that charge inside is equal to 0, right? Okay, that's basically what it's just reminding you there. Okay, the electric field inside a uniformly charged sphere due to those charges. Okay, we're not talking about any other charges elsewhere, but just due to those charges, it all adds up to 0. And we'll actually prove that more formally later in the course. Okay, we just kind of take it as a factoid right now. It essentially has to do with cancellation, right? There's charge on this side making electric field pointing one direction, but that field is canceled by the charge on the other side. Well, if there's 0 electric field and I have a neutral molecule in a region where there's 0 electric field, how's it going to polarize? It's not going to polarize, right? Question. Okay, what if a molecule's not at the center? Well, it is. Okay, it's not at the center, but it says the result is that the electric field basically everywhere inside this sphere is equal to 0. Okay, so even if you're here, or here, or here, or here, or here, if the electric field is 0, then it turns out that there's no polarization. Okay. Now you might ask, well, what if you get really close to the surface, and then things start to break down a little bit, because as we'll see, and you'll actually have a homework problem on this for next time, we say it's a uniform charge distribution, but when you get down to the atomic level, there may be one atom that has an extra electron or an extra ion here, and then very far away from that on an atomic scale, there's another one with an extra electron. And so what looks smooth and uniform at a distance may at the atomic level be kind of non-uniform. Okay, it might be kind of point charges here and there. And so when you're right at the surface, it kind of breaks down. But as long as you get a few atomic diameters away, sort of several nanometers away, you're at a point where that charge distribution looks smooth. The electric field is essentially 0 inside. Polarization is 0. Okay. Okay. If it were a metal sphere, for a metal sphere, first of all, can we have induced dipoles in a metal? No, we're talking about a mobile sea of electrons, right? Not electrons that are bound to individual atoms. Okay, so even drawing dipoles is a bad idea because we're talking about a conductor, not an insulator. But then again, even in this case, what's the net electric field inside? If this is now a metal, net electric field is equal to 0. In fact, for the case of a metal, it doesn't even have to be a sphere, right? It could be any old object. The geometry doesn't matter. And no matter what you have, if you have a metal at static equilibrium, the net electric field inside has got to be equal to 0. Okay? So this this is sort of a geometric property of adding up all the electric fields due to all the charges, and you get this result, which we'll prove later. Has nothing to do with whether it's conductor or insulator. Okay, when you have a conductor, no matter what the charge distribution is, no matter what the shape of the object is, when you're at static equilibrium, that electric field's got to be equal to 0. Okay. Questions? Yes. That's right. Okay, so the issue is superposition of all those 1 over r squared fields. Okay, because you have a point charge here, but you have a point charge here and here and here and here. Yeah. So essentially, kind of a preview of coming attractions. What we'll eventually do in the next chapter is we'll look at how to actually break this up so that if you look at it sort of a segment of this sphere, okay, say at this end, and if this is negatively charged, then the electric field due to that segment is going to be pointing in that direction, right? Okay. The electric field due to the charges everywhere else, if we look at the electric field due to this patch, it's going to be pointing in that direction, and the electric field due to a patch over here is going to be pointing in that direction, and the field contributions due to these segments farther away is going to be smaller, but there's more of them, right? There's more of them, and so I'm not proving this mathematically, but it's just kind of making a plausibility argument of how inside a sphere you can get a situation where the electric fields are all canceling out. Okay, and we'll see this more formally in days to come. Okay. Good question, though. Other questions? All right. Let us then talk a little bit about charging and discharging. How long will it possibly go on? Charging and discharging for conductors and insulators, and we talked a little bit about charging an insulator last time. We talked about for an insulator, charging by contact or rubbing or something like that, where you have surface interactions going on. I showed the example of taking the plastic pipe and then rubbing it with some material. And so we said that there's charge exchange going on, right? Or there's some transfer of electrons. Okay, maybe one object is losing electrons, the other is gaining electrons. It's got to obey conservation of charge, though, right? So if you have one object like the piece of clear plastic pipe, another object the silk, and I were to rub it, then there's some contact interaction where the total charge of the silk plus pipe stays the same, but one gains negative, one becomes more positive due to a transfer of electrons. Or what else could be transferred? We said what couldn't be transferred was what? Bare protons ripped out of the nucleus, right? But we could have a situation where instead of electrons, maybe we had ions. Yeah, ions could be transferred. And the mechanism behind it can get kind of complex and is the subject of a lot of research, particularly with the tape. You have materials that are made of hydrocarbons, long polymer chains, right? And if you have some sort of contact interaction where you rip one surface away from the other, then these polymer chains, these hydrocarbon chains, might be broken in such a way that instead of a neutral molecule, you end up with two ions, right? One ion is positively charged, one negatively charged. And, it's the mechanism behind it. We don't know for sure for any particular situation, but the net effect is the same. Okay, one ends up more positive than the other. Discharging an insulator can be a little bit tricky because Again, if you have an insulator, the charge tends to just stay there. Okay, so if we have an insulator, we can just charge one piece of it. And if you brought an opposite charged particles nearby or an oppositely charged object, you could, if you were able to maintain enough contact, discharge one area, but you can't, for instance, you can't directly get rid of that charge without some sort of contact. There is one method, though, we can use to discharge this piece of tape. So when I was doing the tape experiments earlier in the week, let's see if I can get it charged up. We rip it off, and it's charged up. It's interacting with my hand. So presumably the charge, if there are any extra electrons or extra ions or whatever, they would be on what side of the tape? The sticky side, right? Because that's where the contact interaction is going on. Okay. But then I take my fingers and I rubbed the slick side of the tape and now it's still got a little bit of a charge on it. Let's see if I can get rid of it more. It's so dry in here that's very difficult for charge to spread. Okay, let's see if that worked. Yeah, it's pretty good now. Okay. So what did I do? What happened? I didn't touch the sticky side where presumably there are ions or electrons or something, right? Extra charges on that side. So what did I do? Yes. I put ions on the slick side. Okay, so where do those ions come from? My sweat. Yeah, am I a conductor or an insulator? Yeah, I'm actually a conductor, aren't I? Because you have a layer of sweat, layer of water dissolved on your skin. And dissolved in that, or spread over on your skin, and dissolved in that water are ions, salts, right? So you could have sodium chloride dissolved on the sweat of your skin. So let's say, for example, we had this tape, and let me do it this way. So here's a tape, and let's say we have positive charges on the sticky side of the tape. And then here's my hand. Okay, that's a hand. And dissolved on my skin are ions, right? We have maybe sodium chloride, so we have sodium, positive sodium ions, negative chloride ions. So what's going to happen as I rub my fingers over the sticky side, or the slick side? Chloride ions are going to the tape, right? Because we have these positive charges here. They're creating an electric field that's going to attract any mobile charges. And so we end up with a situation where the mobile charges, these dissolved ions, can actually be affected and be moved by the electric field. And so I'm going to leave behind enough chloride ions on the surface, reducing the net charge of the tape, and therefore reducing the overall electric field that it creates until the electric field it's making goes to zero and it's not attracting any more charge. Okay, so I'm discharging by contact in sort of an indirect way. I still have to touch the entire surface because the surface is an insulator, but I'm a conductor, and so there is a source of mobile charges to discharge the tape in this case. What about, let's see, what else do we want to talk about? What about a conductor? Let's say we have a conductor. And we can charge and discharge by contact, right? So let's talk about charging by contact. And let's say I have some conducting object, some piece of metal or something that already has a charge on it, some positive charge. And I bring another piece of metal nearby, which is originally neutral, and I bring them in contact so they actually touch. So what happens to the charge? It actually gets distributed over the entire object, right? Because why? Why in this case is the charge going to distribute over the entire object? Okay, so it goes to equilibrium, right? It's going to reach equilibrium, and these charges are able to spread because what do we have in a conductor?